too quick.
Happens all of a sudden. We're good to go.
All right. Yeah. Well, yeah, that's what I was hoping All right. I think that's just about everybody from the coffee room. So we'll go ahead and get started here. Once again, my pleasure to introduce one of my students who's working on another sort of favorite topic of mine, which is convection, and trying to understand how different observations can tell us something about it. So today we have Megan Schaaf, who will be giving her master's thesis presentation, looking at deep convection, and in particular trying to use a combination of different radar and radiometer data to try to get at this tough question of precipitation efficiency. But before she begins, just give you a little bit of background on Megan. So she's from Oconomowoc, Wisconsin. I met Megan in, I think it was radar and satellite class when she was an undergraduate here. She got her degree in 2023. That year she started working with me a little bit on looking at high latitude precipitation from some data that we collected from a field project in Helsinki, Finland. Got really proficient at looking at radar data. This is C-band radar data. Also, I think some aircraft data, and trying to connect the dots between flight tracks and ground-based radar and maybe vertically pointing radar on the ground. And then, as far as her master's is concerned, like I said, we kind of shifted into the tropical regions and started to try to see if we could combine data from the, well, I guess it was the Global Precipitation Mission, which is really good at estimating precipitation, with ice information from Cloudsat to try to get at this precipitation efficiency question. Megan has also TA'd for me now, I think 3 times in a row, and she's done a great job on the 441 class. But besides working in TAing, Megan also has some interests that kind of align a little bit with mine as well, in particular kayaking. I love doing that as well. And then another really interesting thing, and I don't know if we're going to get to see a picture today. We often see pictures of people's cats and dogs. Megan has a gecko named Samwise, and I'm really interested in looking at and seeing what the gecko looks like. So with that, I'll go ahead and hand it off to Megan.
Okay, can you guys hear me all right? Okay. So as Tristan mentioned, I'm going to be talking to you guys about the global precipitation efficiency in deep convection from a satellite perspective. So to kind of give you a sense of what I'll be talking about today, naturally I'll be doing my introduction and methodology, but then I'll also introduce 2 of my 6 case studies. There isn't enough time to go into all of them, so I'll kind of introduce those 2 to kind of set the stage for the global analysis portion, and then I'll end with conclusions. So to initially begin, why deep convection? Deep convection is central to Earth's hydrological and radiative cycles. It controls precipitation distribution in both the tropics and the mid-latitudes, and it also strongly influences cloud radiation interactions, as well as climate feedbacks. So to define the precipitation efficiency for you guys, it essentially quantifies how efficiently convection converts condensate into precipitation, rather than maybe being recycled as a water vapor or being lofted as ice. There are multiple definitions to precipitation efficiency. The one we use is in the upper right-hand corner, where it's rain rate over ice water path plus liquid water path. But it should be noted that in the modeling space, this denominator is often replaced with water vapor convergence. But since there is no way of measuring that from a satellite perspective, we use these 2 variables instead in that place. So why are we even looking at it to begin with? Quite a few reasons. It influences rainfall intensity and distribution. It modulates cloud lifetime and radiative forcing. It also has everyday implications of how convection gets represented in climate and weather models. And additionally, it's strongly linked to droplet growth, evaporation, ice processes. And especially with this last one, there is a lot of uncertainty that we have in ice processes in clouds. And so this is a very influential area of research. So So far, we know what we know about precipitation efficiency primarily from models, but also observational data. Models are great because you can kind of manipulate the environment and see how that directly correlates to a change in precipitation efficiency. But the problem with models is they are based on assumptions and idealizations of clouds and ice in the atmosphere, which, as I said in the last slide, is a great uncertainty in our field so far. So I included these two images, courtesy of Sylvia Sullivan in a presentation she gave earlier this year, kind of showing the differences in models and how they perceive rain rate in the top, and then that water vapor convergence in the bottom. And as you can see from model to model, there are sometimes completely opposite signs being predicted. And so there is a great uncertainty in the modeling world. Now, there also have been observational studies, both regional and, ironically, also satellite. But regional studies have used ground-based radar, aircraft, or have been general field campaigns that maybe use a multitude of instruments. And these are great because you get real-world observations of that region, but naturally you can only make assumptions about the globe from looking at one area of our planet. Additionally, satellites, past satellite missions with the focus of precipitation efficiency have kind of been limited either by latitude or by instrumentation. So such as the TRMM, Tropical Rainfall Measurement Mission, that's located obviously just around the tropics, and therefore you can't really get a sense of precipitation efficiency at the mid-latitudes as you can there. So not to rag on models at all, but this is just kind of to emphasize the error that we see in precipitation efficiency using models. And so what we have here is, again, from Sylvia Sullivan's presentation, you have precipitation efficiency on the y-axis and the different types of models on the y, or on the x. And as you can see, there is a ton of error. And not only that, but this y-axis is a logarithmic scale. And so not only do you have a logarithmic scale showing multiple orders of magnitude of error, but you also, in actuality, these errors show much greater.
And is this the same definition of precipitation efficiency that you're using?
Essentially, yes, but again, the denominator is replaced by the water vapor convergence.
No is the answer then?
Yeah.
Yeah, okay.
Okay, so kind of to go into how we get some of these variables and how they get added into the atmosphere, how they get taken out. These are not all the ways, of course, but they're kind of the ones that pertain mostly to this research. So for liquid water path, some sources, condensation of water vapor, something we're all familiar with. As a parcel raises in the atmosphere and cools, it condenses and can form a liquid droplet. Additionally, liquid retention through updrafts, keeping liquid drops aloft, will also keep LWP values pretty high. Some sinks of this would be warm rain processes. So when LWP eventually gets turned into solid precipitation, it naturally rains out, decreasing the LWP. Additionally, the evaporation of droplets. So when a droplet encounters a dry layer of air, it's going to evaporate, decreasing this value. And additionally, the freezing of ice, or the freezing of liquid to ice, will naturally decrease your liquid in the system and increase your ice water path, which, segueing into ice water path, there are tons of different processes behind ice in deep convection. And so to kind of summarize the majority of it without going too in depth, primary and secondary ice nucleation, so essentially is the parcel just freezing up there, whether it be because of a nucleating particle attaching to it or just freezing because of temperature, or are ice crystals colliding and breaking up. That can also be a source of additional ice being created in the atmosphere. Additionally, vapor can also attach itself, can condense right onto ice crystals through depositional growth, and so can liquid, supercooled liquid droplets can also freeze upon impact with ice crystals through riming, and then aggregation when ice kind of sticks together. All of these things increase your ice water path. Additionally, the advection from anvils. So when you have particularly strong when you have particularly strong updrafts, you do get a lot of ice aloft, and when that is inserted into the anvil can often increase the lifetime of ice in the convective system for quite a bit, even after some of the main convective portions have died down. And so some sinks of this, naturally melting. I'm not going to go into that one. I think all of you are aware. And then sublimation, when ice comes into contact with the dry layer, this also can cause it to sublimate and transform into a vapor. Additionally, the sedimentation of large particles such as hail, graupel, and snowflakes can all remove IWP from a system. So how does this relate to some of the things we see in deep convection? So updraft strength, in general, strong updrafts lead to increase in LWP and IWP simultaneously, because updrafts can both loft droplets to stay in the cloud before raining out, and they can also loft supercool drops to the point of freezing in the upper portions of our atmosphere. Entrainment and mixing tends to have a negative effect on both variables. Dry air mixing is going to cause both evaporation and sublimation for each of these respectively. And then storm organization. Again, what I was saying about anvils, when ice is lofted into an anvil, that can increase your IWP, keep it up there for longer. But storm organization actually kind of has a mixed effect with liquid water path, because LWP inside of a convective core can often be decreased because either the updraft is lofting ice too quickly before it can fall out, or it can also, again, loft liquid. But then, depending on how the convective cell is kind of organized, it can also move liquid into more stratiform regions, which is a cloud known to be able to harbor large amounts of liquid water for a while. And so, to kind of summarize all of that, the liquid water path is mostly dominated by condensation and warm marine removal. It's strongly sensitive to updrafts and entrainment. Ice water path is dominated by freezing, riming, and deposition, and it's strongly linked to storm depth and organization. So this leads to the greater question of the motivation behind this work, of how do these processes lead to a variable PE? And so the first thing that we kind of wanted to look at were latitudinal differences. And so the subtropics, we know convection here is, or subtropics and tropics, I should say, we know the convection here is thermodynamically driven, more moisture rich, and there's going to be high IWP because these extend very high into the troposphere, since the tropopause is much higher there. And so this, due to the warm, moist environment, we expect there to be less evaporation and subsequently more efficient rainout and higher PE. The mid-latitudes, we know, are more dynamically forced convection. Fronts, shears, they're often mixed phase clouds, and are part of kind of these larger, again, synoptic systems. And so due to the drier air that we see at the mid-latitudes, as well as the stronger entrainment, we do anticipate there to be a lower precipitation efficiency here. So some kind of smaller questions that I had when going through my research include, one, are there latitudinal differences between PE at the mid-latitudes and the tropics? Two, what conditions influence PE in each region? Three, how linked are PE and cloud radiative properties? And then four, do large-scale motions such as the Walker circulation play a role in PE? Okay, so we do have a lot of instruments and data sets to go through. So starting off simple with Cloudsat, it's a member of the A-Train constellation. It is polar orbiting, and it contains the CPR, the 94 gigahertz cloud profiling radar, which is a W-band radar, which is very high frequency and made to see light precipitation and ice. It does, however, have difficulty seeing near-surface precipitation because of attenuation, since it is a higher frequency. That is where GPM, the Global Precipitation Measurement mission, comes into play, because this has two instruments of interest, the dual frequency precipitation radar, the DPR, which has KU and KA band radars. Both are larger frequencies than Cloudsat is, and so they're really great at picking up surface precipitation and convective intensity. Additionally, there's also the GMI, the GPM microwave imager, and both of these instruments, or this entire satellite, covers from 65 south to 65 north. So Joe Turk at JPL decided, since Cloudsat can see all that stuff aloft and GPM can see all that stuff at the surface, why don't you combine them and kind of get a better idea of what's going on in convection? And so I took this image from Battaglia et al. In 2020 to kind of show you that, okay, this blue region is where Cloudsat is seeing, and this green region is where GPM is seeing. And so individually, you can maybe get some information about those respective areas in the cloud, but you can't really see the entire picture. And so when you combine all of these wavelengths, you actually get this dark gray region. And although you might not see the entirety of the convection yet, you can still see a greater amount than if you were to use them independently. So this is an incredibly complicated process that Joe Turk went through to create this data set. But essentially, all you kind of need to know about this is these green, red, and blue dots are representative of the DPR, and then these kind of like light blue swath colors are indicative of the GMI path. And so what he does is kind of look to see where these paths intersect with the Cloudsat curtain. And if they intersect at any point within 15 minutes of one another, and there's something going on beneath, not necessarily convection, but something, he'll save that as a part of the data set. Now, we're also going to be merging this with Juliet Paluski's Convective Object Database, which uses A-train observations to kind of unify all the instruments of this constellation into one location, and on top of that, be able to do it for convective events all over the globe for the years of operation. And so, although there are more measurements than just Cloudsat and Aqua, those are the main satellites we're going to be using from Juliet's database. And essentially, Cloudsat is going to be our unifying factor. So wherever Joe Turk's data set picks up something, we know that the Convective Object Database will also see that because of Cloudsat. So another super complicated process of how this was made, but essentially it stems from an algorithm developed by Tristan, identifying where convective cores are along the Cloudsat pixel. And essentially, just wherever you see these peaks in reflectivity is kind of how these cores were identified. Then what Juliet essentially did was kind of group those cores with other surrounding convective flags that are found within Cloudsat. And she had a lot of other stipulations, but again, not enough time to go into them. But essentially, she did have requirements of what includes convection and what gets dropped from convection, and that's how she got her Convective Object Database. This image here is to show you for the 2 years we're looking at, 2014 to 2016, the instances of deep and shallow convection around the globe using her database. One thing I did just want to note is that throughout this presentation, DPR from GPM and AMSR from Aqua are kind of used interchangeably. They are kind of treated as if they're the same, even though we do know they're not. And this kind of shows their relationship here. They don't have a perfect one-to-one relationship, but they are close enough where they can still provide meaningful information to us about the rain rate. Additionally, it also should be noted that their relationship is closer over ocean than it is over land. That's where stuff kind of gets a little wonky. But again, just know that whenever GPM isn't available, AMSR is kind of taking its place. Okay, and again, there's not enough time to fully go into the retrieval mechanisms for each of these satellites, but this is where each of the variables are coming from to kind of put together our precipitation efficiency equation. GPM is providing our rain rate through looking at brightness temperatures, essentially. Cloudsat is providing our ice-water path by looking at ice-water content in the atmosphere, and AMSR is providing our liquid water content by essentially looking at the specific humidity. And again, like I said before, whenever GPM isn't available to provide that rain rate, AMSR will be filling this. They do have technically different retrieval algorithms, but they do both stem from brightness temperature and are similar in that regard. Okay, so as I mentioned with Joe Turk's data set, the GPM Cloudsat coincidence data set, it's not necessarily convection that's happening in these coincidences. So to kind of separate out deep convection from shallow convection, we followed the same stipulations that Juliet had in her convective object database, where deep convection is anything greater than or equal to 8 kilometers, and shallow is just anything below that. And then this is kind of our final, I guess, number of convective events that we have that the Cloudsat and GPM intersection data was able to pick up for the 2 years that we're looking at. So how we kind of begin to choose the regions that we'll be looking at and the cases that we're looking at was based on this plot here showing where the concentrations of convective objects are in this database. And as you can see, they're mostly concentrated around the tropics, especially in the maritime continent and stemming down to Brazil. We also pick some mid-latitude cases, which I will be getting into here. So for the tropics, we wanted to have 2 of our cases associated with the Walker circulation, as that's a big part of tropical convection. And so our case 5 and our case 6 are associated with the main descending and ascending branches of the Walker circulation. We also wanted to have some sort of latitude variance. And so most of our cases, 4 of our cases, are in the tropics. We also have 2 in the mid-latitudes, 1 in the Great Plains and 1 in Argentina, both areas known for very intense convection. It should also be noted that the specific case studies I chose that you'll be seeing today and also just in my thesis, they are multi-core convective events, and they were chosen because they have that quality and they also have some sort of anvil. But when I'm actually doing the analysis of all the points within those case boxes, there is no stipulation that they have to have a minimum core requirement or a minimum anvil fraction. So just keep that in mind. Additionally, as you'll probably notice, kind of when we say mid-latitude, we are also saying land, and when we're saying tropical, we are saying ocean. And so we just didn't have enough time in this research to kind of evaluate the latitudinal differences and the land versus sea differences. And so essentially the thinking was, okay, most of the land is in the mid-latitudes and our tropics are mostly ocean. And so we follow that. So there will be a brief mention of kind of ocean and land contributions, but ultimately no formal analysis of land versus ocean. Then finally, before getting into the case studies, I do kind of want to point out that naturally, due to how our planet is, there's not going to be the same amount of objects in every single box. And this is because that the tropics do just experience more convection. And so our mid-latitude cases have only maybe a couple hundred instances where our tropics can experience a couple thousand. Okay, so now kind of introducing the case studies. Again, there's not going to be any real formal analysis of the case studies. It's more to set the stage for what we'll be talking about in the global analysis and to kind of show you guys what we're kind of looking at. So the case studies do use the Cloudsat GPM dataset merged with the convective object database. And our case 2 is the first one that I'm going to kind of focus on. This is in our Great Plains, specifically our western Great Plains over Colorado. And this is kind of just the larger scene at play. But what we kind of expect for this region is we do expect a strong vertical shear, more tilted updrafts, which lead to longer storm lifetimes and more ice lofting. And subsequently, we do expect lower precipitation efficiency because of this. Most of the moisture from this area is coming from the Gulf, and it's more synoptically and mesoscale forced. And additionally, this isn't true for the entire case box, since it does take place over the entire, or not the entire, but a good chunk of the Great Plains, is there might be orographic lift with this specific case, because it is just to the east of the Rockies, which you can kind of see the terrain here at the bottom of the reflectivity profile. But yes, so essentially what you're looking at is a vertical reflectivity profile of this specific case. And what you'll notice is there's this little star. And what this is representative of is the RCOG, which is the relative center of gravity. This is a very complex equation, or not necessarily equation, but variable that was calculated by Juliet Paluski. And essentially what it's saying is this is the point altitudinally where half of the stuff in the convective system is above this point and half of it is below. And so since we don't have any updraft or intensity variables available to us, we do use the RCOG as kind of a proxy for updraft, with the idea that, okay, stronger updrafts are more likely going to push half of the stuff up higher. So, kind of how we're able to visualize some of this data associated with this storm is we're able to look at the altitudinal distribution of ice and liquid. Our ice, it peaks at about 7 kilometers. We also do see a little bit of a peak of our liquid there, but naturally, as you would expect, the liquid's towards the bottom, ice is towards the top. Additionally, this specific case had a very interesting shear profile. Now, all the cases that I've looked at, this one did have the largest shear associated with it. Yet what's interesting about it is it has near negligible surface shear, and it has very minimal upper level shear. And ultimately, that total shear is getting its magnitude from mid-level shear, which is interesting for reasons I will point out later. Okay. So now, what this is both of these are along the Cloudsat curtain. And so you can kind of see that when our storm, if you're looking on the right, kind of tapers off into an anvil and ice content decreases and whatnot, you kind of see this warming effect in our CRE plot down here. Now the cloud radiative effect plot will be shaded blue when it has a net cooling effect, and it will be shaded red when it has a net warming effect. So you can see for the most part that this cloud actually is mostly cooling, but we do see this region of red that is also associated with the area where the cloud stops precipitating. And so there is this clear relationship between precipitation and radiation that is the ultimate goal of this research, is to kind of quantify that, because this is a trend that shows up in all of the cases that we look at.
Wait, so can you say that again? I missed the connection between the radiation and the precipitation.
Yeah, so
the short wave and long wave effects.
yeah, so this plot is just showing you like if it's cooling or if it's warming, and you can see, okay, the red here is the rain, and so when the rain stops, we start having that warming effect. And so we're looking to kind of quantify that relationship.
The cloud, it's the total cloud radiative effect is the light gray line on the bottom,
yes,
and the top is the rain rate.
Correct.
The red and blue jumped out at me, so that's why
yes.
I was confused. Thanks.
Okay, so the next one I'll be looking at is case study 5, which is taken in our Eastern Pacific Ocean, the descending branch of the Walker circulation during the La Nina year. And what we kind of expect for this area is limited vertical shear. I don't include a shear profile in the next slides, but it's very unimpressive. There's barely any shear there. And also, we do expect deep and vertical convection with strong cores and ice-rich anvils. And so, this is what we end up getting for this case. The first thing I want to note is the precipitation efficiency associated with this specific case. In case you saw, the last Great Plains case had a precipitation efficiency of 0.3. And now this one is of 2.3, which is kind of what we expected, considering what I discussed earlier about the latitudinal variations. On top of that, the RCOG is only a little slightly higher than our Great Plains case at 8 kilometers-ish, maybe 9, where our Great Plains was more so around like 7, 7.5. But the feature of interest that really stood out to me is this intense reflectivity that expands into the upper troposphere. And now we know that this isn't going to be a high concentration of liquid or anything like that, so we kind of anticipate there to be a ton of ice being wafted into the upper troposphere, which is exactly what we see. And now for reference, when I was doing all of these plots for all the different cases, a lot of the ranges were typically between like 300 to maybe 800 milligrams per meters cubed. But this one has ice contents all the way up to 1750. So a ton of ice in this system. And corresponding to that, we do see that our ice water path doubles in value compared to our Great Plains case. So now going into the global analysis, we will be getting rid of the GPM Cloudsat coincidence data set, and instead just focusing on Juliet's convective object database. And that is because, just to remind you, that with the GPM Cloudsat interface, we only had about 450 convective objects globally, maybe only 5 or 6 in each region that we were looking at. And so this doesn't provide a ton of great and reliable statistics when taking that into consideration. And so with Juliet's convective object database, we actually have 6,100 COs just in our boxes alone, not even including the rest of the globe. So before getting into this next plot, I do just want to point out that the boxes themselves, the bar plots themselves, represent the average of all the cases that are within each box. It's the little black points that represent the individual case studies that we looked at. And so, these first 2 cases are our mid-latitudes, and the last 4 are tropics. And you can kind of see that across the board, the tropics have greater magnitude in each one of these boxes, or each one of these variables. And another thing that I kind of wanted to point out about this is kind of what I was discussing before, talking about kind of land-sea variation. We can see here that our tropics, which are a mix of purely ocean and then kind of coastal and like land cases, there actually isn't that much of a difference between them. And so with this in mind, we can safely say that there are latitudinal variations because any variations that come from land versus ocean in these cases are minimal enough where you can still see the grouping of mid-latitudes and tropics. So the next thing I kind of did was break up our precipitation efficiency equation into the ice and liquid components. Now this isn't mathematically feasible, these things cannot add up together, but they do give you a sense of kind of the efficiency regarding liquid and regarding ice. And so what we can see, again, is our tropical cases are all very similar regarding the liquid efficiency and ice efficiency values. And we can see that our mid-latitude cases are not only different from the tropics, but they're also very different from one another. And so kind of revisualizing this plot, we can look at precipitation efficiency for what it is as an efficiency. You know, how fast are these things raining out? And so again, tropics all the same, the efficiencies all the same, but we see that case 1 and case 2 have similar ice efficiencies, but case 2 has a much, much larger liquid efficiency than we see in case 1. Diving a little deeper into kind of why this is, because again, our precipitation efficiencies for these cases are incredibly similar, yet we see a very different efficiency when you break them up by liquid and ice components. So kind of looking at this further, I made a violin plot of kind of the distribution of RCOG averaged across all of these case boxes. And so, as you can see, our case 2, our Great Plains case, actually has way more in common with the tropics than it does case 1 in Argentina. And so after really talking with both Tristan and Angela about this, we kind of came to the consensus that the reason this could be, because technically case 1 does have values reaching upwards of 12 kilometers. The highest distribution is actually between 2 and 6 kilometers. And so the general thought is maybe, even though Argentina is known for very intense convection, the specific area that we chose is where a lot of it starts. And so that brings in another idea that we didn't really consider going into this research of the importance of life cycle when it comes to the precipitation efficiency. So, kind of switching gears a little bit, I wanted to introduce kind of a new variable. So this plot is meant to show kind of like the correlation of the minimal environmental variables that we have down here and how they kind of relate to the variables we're looking at for precipitation efficiency. And the one new variable I wanted to introduce is anvil fraction, which is the fraction of the convective object that is not precipitating. And so, naturally, the higher the anvil fraction that you have, the lower your precipitation efficiency would be, we're expecting, because all that stuff is getting lofted into the anvil rather than being potentially rained out. Now, you can kind of see already some trends with things averaged, but what we really want to see is kind of the specific areas. And so, again, you can see some commonalities. You can see that overall, shear doesn't really play a role except in our Great Plains, which I will get to in a moment. But then, we can use this to kind of answer what conditions really do influence precipitation efficiency in each region. And so what we can kind of see across the board is anvil fraction is negatively correlated to the LWP and the rain rate in every single case, which makes sense because, again, the more you're lofting up as ice, the less that the less moisture that is available for the liquid water path, and subsequently the less that's going to get rained out. Additionally, we also see that RCOG is positively correlated with ice water path in every single case. Again, this makes sense because stronger updrafts, stronger intensity of convection is going to have those ice crystals lofting and increasing our IWP. Now, what is interesting is that our precipitation efficiency is actually negatively correlated to all levels of shear in our Great Plains. Now you can see in every single other area, it's not really one way or the other, maybe a slight correlation, but overall not very significant. And why this is especially interesting is, okay, you remember the shear profile I showed you from the Great Plains? Well, Argentina, although I didn't show it, had a very similar total shear magnitude. They were very similar, but just where the shear was distributed was different. And so this kind of begs the question of, okay, maybe it's not necessarily shear that is influencing PE, the magnitude of it, but maybe there's a component of how it's actually organized that mostly impacts the precipitation efficiency. But the fact that PE is negatively associated with shear isn't super surprising. It could be due to tilted updraft, causing raindrops to fall out into dry air. It could be caused by strong downdrafts taking moisture away from the updraft, or this just is a region with increased entrainment, which will naturally lead to a decrease in the precipitation efficiency. However, it's this positive correlation that you see with the shear, with LWP, that kind of makes me think that the shear is, there are shear processes going on that are lofting the condensate up and therefore increasing our LWP, but decreasing our precipitation efficiency since it's not being rained out. And then I did kind of want to zoom in on this anvil fraction variable I introduced to kind of answer this question of how linked are PE and cloud radiative properties. So as you can see just initially, there is a relationship between the total anvil fraction and the precipitation efficiency. And again, this is because as you increase the total anvil fraction, that means more and more ice is getting lofted, and your precipitation efficiency is decreasing because that stuff cannot be rained out. And so this kind of is where we want to introduce the idea of using the net CRE, that plot you guys saw before, this relationship between precipitation and radiation, and use that to quantify what we're seeing here in this relationship. So this is the one piece that we are missing from this research that I will need to continue. But essentially, that's kind of the next mode of the plan for this. And while we're not able to quantitatively explain this relationship yet, we still can get information from the regression slopes themselves. And I guess, okay, before we go into this, I want to remind you guys that our case 5 is associated with our main descending branch, and our case 6 is associated with our main ascending branch of the Walker circulation. And what you can see here is that these slopes, for our descending branch, it has the most intense gradient, and our ascending branch has one of the smallest gradients. Another important thing to kind of realize about this plot is that there's not really a relationship with latitude here. So this sensitivity between the total anvil fraction and then the precipitation efficiency does not appear to have kind of a latitudinal trend from what we've seen. Additionally, I guess even though we didn't have the variables available to kind of evaluate specifically what's going on in our case 5 and case 6, we can kind of use the information we know about the Walker circulation to kind of diagnose why this is to begin with. And since our cases were taken over La Nina years, we know that La Nina strengthens the gradient of the Walker circulation, making the Western Pacific have higher sea surface temperatures, more intense updrafts, a lot more moisture over there, whereas our Eastern Pacific is a lot more dry, cooler surface, sea surface temperatures, and less intense convection. And so my kind of running theory about why this might be arising because of the Walker circulation is because we know, because of this plot, that regardless of where you are, as you increase your total annual fraction, you're going to be decreasing your precipitation efficiency. But if you're in an area with drier than normal conditions, we can assume that this relationship is going to be more sensitive, because as you're lofting things into the anvil, you're taking moisture from an already moisture depleted environment away from potentially the liquid water path and subsequently the precipitation efficiency. And so this kind of answers the question of, do large-scale motions such as the Walker circulation play a role in PE? Now, while this is only kind of one plot showing it, this wasn't really something we expected to find, and it does prompt that there is potentially something there where large-scale motions should also be considered when considering the precipitation efficiency. Oh, yes.
Sorry, Megan.
No, you're totally good.
Go
Okay.
ahead. I'll keep my question.
Okay. So I talked about a ton of different things today, but to kind of summarize the key points, we did find that there were latitudinal differences between the tropics and the mid-latitudes. Additionally, RCOG and shear show an influence in PE, obviously region dependent. Also, there is the consideration of, okay, maybe it isn't shear magnitude that's influencing the PE as much as the organization of the shear. Additionally, PE and radiative properties show some sort of relationship. We know that. It seems to be a strong one. But the numerical extent is to be determined in my next steps. Additionally, large-scale motions do play a role in the precipitation efficiency and can cause more variability in kind of that sensitivity than latitudinal variations. Okay, so my personal next steps, Tristan and I kind of want to expand what we're looking at, and we have to work with Juliet on this to incorporate MERA2 data, which I believe is part of A-Train, I think Aqua, maybe. And this would allow us to look at temperature, cape, and updraft velocity to kind of get a better idea of some of the convective variables associated with these storms and kind of see those correlations there. Additionally, we do want to do a larger temporal sampling, maybe not all of these years, but we do want to increase the time that we're looking at, increasing the number of points we have to do statistics with. And additionally, as I've said a couple times before, we do want to connect PE to the cloud radiative effect, ultimately trying to quantify the PE and kind of where there's warming and where there's cooling. So personal limitations of kind of this research, not including kind of the data sets that I looked at, there is no consideration of life cycle stage, and this has proven to be very important because our case 1 was completely an outlier compared to all of our other cases. Additionally, we do have latitude linked with land versus sea currently. It didn't prove to be a huge problem for the purposes of our research, but there should be a more formal analysis, kind of as I say here, of land versus ocean. Potential other pathways for this work would be to look at a diurnal cycle that isn't evaluated in this. Additionally, distinguishing between multi and single core convection is important because even in just my time working with this data, I could see that there are differences with LWP and IWP when it's single versus multi-core. We just didn't have enough time to kind of add that analysis. Additionally, any seasonal or climatological variations would also be important, especially if there is that relationship with large-scale motions to PE. So, acknowledgements. Thank you very much, Tristan, for being my advisor for all these years and all the help. Thank you to my committee, especially Angela. You have been wonderful in kind of organizing my thoughts for this. Additionally, thank you to Juliet and Marion for all the coding help over the years, my friends and family, and then also my 2 cats, Thomas and Goose, and my gecko, Samwise. There he is.
Are you okay calling on people?
Oh, sure, yeah.
You start with earlier career or students. Open up the floor then to everybody.
Yep.
Yeah, Megan, really interesting. I'm drawn to your slope graph that was near the end. That's why I put my hand up.
Okay.
And
Oh,
you
sorry.
draw attention to, you know, the large scale of the substance in the water circulation. The other thing, those two slopes, the East Pacific and the Great Plains are almost identical. And they might also share the negatively buoyant downdrafts because of the nature of their environments. I wonder if that's an alternative way to explain some of the similarities that you see in this diagram.
Yeah, and that is something that I have been like kind of personally interested in, is how different these slopes are from one another. You would kind of expect to see more of a mid-latitude tropical difference, especially with some of the other stuff that we have seen. But yeah, that was kind of a personal interest of kind of diving into why specifically these are so different.
Yeah. And then the Argentina case could also be, maybe not the time you sampled it because it's a life cycle thing, but it seems to me it could also be an environment that has really strong negatively buoyant downdrafts
That's
at
true.
some point in the life cycle. And maybe it changes its slope if you catch it 12 hours later or something. So that's interesting. Thanks.
Yes.
Really interesting talk. It's a really interesting data set that you have there, these precipitation efficiencies. I was curious, it kind of went by fast. You had some reasoning about how entrainment affects this quantity. And I'm just thinking, like, I would think entrainment would decrease liquid water because you have evaporation of liquid water, but it would also decrease rain rate because you have less buoyancy because of that evaporation. So what was kind of your reasoning about how the kind of those two are changing and why, like, I didn't even, how entrainment would influence the precipitation efficiency?
So if I'm understanding your question correctly, I guess how I was perceiving that was entrainment will mix in like dry air and can cause the liquid water path to have droplets, or droplets that are evaporating, and so they can't actually rain out. So I didn't really take into consideration the rain rate itself. You know, as it's falling out, it can also evaporate or anything like that. But I guess that's how I was looking at it.
Entrainment has big impacts on the rain rate too, right? So in environmental humidity too, so some of the like east-west Pacific stuff that you were relating to environmental humidity and the entrainment effect might also be affected by how the precipitation is changing in how your numerator is changing.
Yes.
So that's what I usually think about, so that's why I didn't quite follow the.
Yeah, sorry about that.
Yeah, no worries. Cool data set and nice talk though.
Thank you.
I think that one other thing you can see on this plot is that it's obviously very complicated with a lot of different factors. So life cycle, but also there's many other environmental factors that probably go into this.
Yes.
It's nice that we have a big statistical pool of data to look at, but I think the interpretation takes a lot of thought, so.
Guys, can I go?
Yes.
What about mid-latitude oceans? Is there any chance that you might look at a mid-latitude ocean case? Because the convective object, there's plenty of them over the oceans.
Yeah, so they are there. They are there. We just didn't, because again, not enough time to also evaluate land versus ocean changes on top of everything we were also looking at. But yeah, there are cases to actually do that.
So I think that might allow you to get at some of the, they're probably not unrelated. Life cycle and location are probably somewhat related to each other, you know, because this West Pacific Great Plains thing, or East Pacific Great Plains thing, is interesting.
No, I agree. And I guess kind of the purpose of this wasn't necessarily to answer all the questions, but the data set that Joe Turk uses is very underused. And so to kind of show what it can do was kind of the purpose of this. Not, I guess, to answer every single question we have, but potentially maybe someday.
I don't want to hog the floor, but I was also going to ask, so the radiative connection, so it seems like it makes sense to me why total anvil fraction would affect the radiation, right?
Yes.
Because anvils are like high and thin, so those are warming clouds.
Yes.
So the higher anvil fraction you have, the more of a warming effect you have. Is there anything like independent of that you would expect? Like, is that why you expect a radiative connection, or is there any other kind of reason?
So yeah, that connection is very intuitive, but I guess the next steps is more to like quantify how much, I guess. So based on precipitation efficiency of a given cloud, you know, how much is there going to be warming, how much is there going to be cooling, rather than, I don't know, does that make sense?
Yeah. I was just wondering, am I thinking about the reason for the connection? Right,
Absolutely,
okay.
yeah. But the cloud optical depth, which is kind of in the,
Yeah.
the caption there is very important, and whether or not
Yeah.
it's thick anvil versus thin anvil, because this is just anvil fraction, right?
Yeah, so this is all of the optical
Yeah,
depths
so the greater than
combined.
3 could actually be cooling, and so I think maybe a more, discrete version of this figure, which relates to the different pieces of anvil would be important.
Yes.
Okay, cool, yeah, it's cool to make the connection between this and cloud radiative effects. I think that's a neat step to take. So yeah, I think you're onto something there.
Any other questions from the room? Yeah.
You mentioned at the beginning that when models try to represent precipitation efficiency, it seems to be really all over the place. I'm curious if you've given any thought to looking at the models, seeing how they perform, and comparing them to the observations, and seeing if that can tell you anything about what those models are doing correctly or incorrectly, and how that can better inform both model development as well as maybe some additional satellite imagery.
Well, and that would be very interesting because a lot of modeling studies do look at globally, and so you could see where each model is getting it wrong in certain areas of the globe and kind of compare that to what we actually see, and that would be very interesting work, yeah.
As a follow-up to that, and this is related to Larissa's first question, are there modeling studies that use this definition of precipitation efficiency, or how would the different definitions affect a comparison against a model?
So,
They do, okay.
It'd be very different.
Oh, it would be very different,
You
yeah,
couldn't
that's,
have the order of magnitudes, right, because
No.
they're tuning their liquid and
Yeah.
ice water path and their precipitation, right, so
yeah.
you wouldn't get different orders of magnitude, I don't think, for this definition of precipitation efficiency.
Yeah, there's like just to jump in, there's a really good review paper Meg and I were talking about of like trying to summarize all the different ways models and observations calculate precipitation efficiency.
Right.
And so that would be good to look at because I don't think there's very many commonalities of what both models and obs do, but within model versus ob, there's also so many different ways, whether it's the large like water in, condensate out, or actually trying to dive into the microphysics. And so that's such a good point, something we were trying to figure out, like, there's so many different definitions and it's hard to compare apples to
So I
apples.
feel like that's an important caveat on your question,
Exactly.
and that it
Yeah.
will be a challenge to do that.
Yeah,
Major
it's just really hard, yeah.
Okay, if that's all the questions, then we'll thank Megan again for an excellent